introduce yourself, Andrey.
I'm Andrey Grachev, and this is Ola Persson. We both work in Cooperative Institute for Research in Environment Sciences, series, and in the same time we are working for NOAA Physical Science Division here in Boulder. And this project is associated with Arctic climate research and based on terrestrial sites located in Canada, United States, Alaska, Russia, and some other sites on north of Europe. And we look on surface heat budget, different fluxes measured in situ from towers like you saw on the previous slide. And this project allows us to better understand what is heat balance on the surface, because it's more important for changing climate and its boundary conditions for different numerical models like regional or climate. And very important to have correct parameterization, to have correct, physically correct fluxes which included in models.
Okay.
And Ola will present some stuff from our project or from previous projects.
Yeah. So I'm Ola Persson, and what I will present is I'm going to present some data and analysis from the project that Andrey and I are on, but I'm also want to step back a little bit and have a little bit of broader view of how this fits into the larger picture, and try to address some of these questions that I've listed here. And I've tried to organize the presentation according to this line. I've got a lot of slides. Some of them are mostly just pictures, so I'm going to flip through those fairly quickly. But it's to set both the environment, and so you visually can see what the Arctic looks like, and also how some of the measurements are being made, some of the remote sensors and other types of instruments that are used. And it's not just, though I'm an atmospheric scientist, I'll have an atmospheric-centric view of some of the results. I will try to include some things from oceanography and from the cryospheric people who study the snow and ice. And so to better understand the whole system, because the Arctic, the atmosphere, the sea ice, the surface, the land, the soil, and the ocean is a system. And also you should probably put in the biosphere there as well. It's a whole system. And there's a lot of interactions, and that's kind of the main point I want to try to make in this presentation, and I hope I succeed in doing that. So here are some of the main questions that I want to try to address. And so where is the Arctic? What countries are part of the Arctic? How big is it? What does it look like? And does anyone live there? And this happens to be a scientist walking through it, but no, this is actually Matt Schupa, somebody else in our group. So, where is the Arctic? Well, Arctic obviously is surrounding the North Pole being right here in the middle of this picture. And there's a lot of different definitions of what the Arctic is. One definition that some people use is it's everything north of the Arctic Circle, which is this dotted line. And so if we take that definition, you see that the center of the Arctic is basically an ocean. It is an ocean. And it's mostly sea ice covered, at least for much of the year. And there is some land around the periphery of this Arctic Ocean, and there are some settlements on that land also. So, those settlements include some, what you probably call cities, mostly villages, and also some research stations, military stations, those kind of things. I also want to mention that there is what's called an Arctic Council, which is an intergovernmental forum, and the members are Canada, Denmark, because they control Greenland, Finland, Iceland, Norway, Russia, Sweden, and the United States. And there's also some observers to this Arctic Council, and that's in the light blue here. China and India, interestingly, are part of observers to that. All the European countries are observers, and also Japan. How big is it? Well, the United States basically fits within the Arctic Ocean. So that gives you an idea. I want to point out that with the exception of one Russian ice drifting station that's typically there, and also some buoys, ice buoys people put out, there are no observations in the entire Arctic Ocean. No atmospheric soundings, anything like that. We're relying on satellites, basically, over the entire Arctic Ocean. The land sites, however, we do have some measurements, some balloon measurements, for instance, in the atmosphere. And I'll get to that in a bit. So what does it look like? Well, the sea ice, of course, is a very important part of the Arctic, as I mentioned. And so it has an annual cycle. In March, which is kind of its largest extent, the entire Arctic Ocean pretty much is filled by sea ice, with exception of the Norwegian Sea and the Barents Sea here, because of the Gulf Stream affecting that region. But the sea ice actually extends out through the Bering Strait and along the east coast of Asia, and also along the coast of Labrador, and of course Hudson Bay, an entire Canadian archipelago. That's the maximum extent each year. September each year is melted way back. And now, in the last decade or so, we're down to having open water within the Arctic Ocean along the coastlines in September. And I will get back to the September sea ice extent in a little bit here, because that's what people are usually measuring. So what's it look like there? Well, this is a picture I took flying in a small aircraft over the Beaufort sea ice. Actually happens to be in the 1990s, so it was a little bit before the large melt-offs that have occurred recently. But nevertheless, it shows the idea of what it looks like. Sea ice is up to maybe 10 feet thick, but a little bit thinner nowadays. I'll get to that in a little bit too. And it's basically flat with some ridges that might be 8 to 15 feet high above the sea ice itself. To get a scale here, here's a cluster of probably 25 or 30 tents on the sea ice. That's where we just took off from in this aircraft. So we landed and took off from the sea ice. And below the sea ice here, so it's 7 to 10 feet of ice. Then below the sea ice is about 4,000 meters of water down to the bottom of the Arctic Ocean. So this sea ice is a very thin layer, but it's very important. It's often broken up by what's called leads. These can extend for very long distances, hundreds of miles or hundreds of kilometers. Their width can be just a few tens of meters across, or up to maybe a couple kilometers in width. They may last for a few hours or even a couple weeks. And they're basically separating two different ice flows, and the flows may come together or open up. And that's part of ice dynamics. At Kreiswerk, people study ice dynamics quite a bit and try to understand what causes these leads and both close and to open. During the summer, the individual flows are more easily distinguishable because they're often surrounded by some leads, a little bit of open water, rather than being frozen together like they are typically in late winter. And they can have different sizes. This flow is roughly around 5 miles in diameter, but that gives you an idea that there's a lot of range in the sizes of the ice flows. And they're moving around, and especially when they start getting open water around them, then they're almost independent. But there's, of course, enough of them here, the density is enough, so they do impact each other as well. Over the land areas, on the Canadian side, the Canadian archipelago, Greenland, so maybe I should say the Western Hemisphere, until you get to Alaska, it's typically fairly rugged. And there's typically ice caps on these mountains that are a couple thousand meters high, and with glaciers coming off of them. This happens to be on Axel Heiberg Island in the Canadian archipelago. This is Ellesmere Island, which is next door to Axel Heiberg Island, where Eureka is located. The flux tower is right there. So it's a beautiful spot, actually. But the point is here that there's a lot of complex terrain. There's tundra, but in this case, complex terrain tundra. You can see some grasses, and you can get an idea here that this area looks a lot like the tundra up in the mountains here. It's very similar when you get above tree line. One thing that's much different than down at these lower latitudes is that you have darkness. This is a photograph I took in late February at Alert, also on Ellesmere Island. And this was noon, looking south. Sun hasn't risen. And so this is the lightest it had been for 4 months. About a week earlier, it didn't even get light at all. It was totally dark and had been dark for at least 3 months before. And so there's a large period of darkness. In the spring and the fall, there's the diurnal cycle, the typical diurnal cycle you see. But then in the summer, it's all light pretty much. There is some changes in solar radiation unless you're right at the North Pole. So there's some diurnal cycle, but it doesn't go down. It doesn't ever not have any solar radiation. And, of course, temperatures can be quite cold. And Alert tends to have a fair bit of snow, as in contrast to some other places like Eureka, which typically does not. Other places, there's much more tundra, much more vegetation. This is Tixie. Some terrain there also, but it's much more lush and grassy. And this is the tundra outside of Barrow. And a lot of muskegs are these little lakes. It's very marshy and very difficult to walk through. And so it kind of gives you an idea of what some of these areas look like. Are there people living there? Yes. There's some small towns or villages. New-Ålesund on Svalbard, population 35. Resolute up in Canada, 229. Little larger one, Clyde River, which is also in the Canadian archipelago. Alert has a permanent population of 0, but it is a military station. And then there are some bigger ones. Dead Horse in Alaska, only permanent population of 40, but because of Prudhoe Bay being in the area, it can be up to 3,000 people at times. Barrow, over 4,000 people. Tixie, Russia, used to have over 11,000 people. Now is down to about 5,000. And Murmansk, over 300,000. Murmansk, of course, is in the area where the sea ice doesn't extend in the wintertime near the Barents Sea. So that's why it's a port town. And also what lives up there, wildlife. Musk oxen. This is again on Ellesmere Island at Eureka. Arctic hares, the herds of them. Lemmings, Arctic foxes. Wolves. And they're very curious. These are tracks around one of the Eureka Tower. And we'd gone in for lunch, came back, and full of tracks. And, of course, polar bears, and especially on the sea ice. That's where they are king, and that's their hunting grounds. When we go out on the sea ice, we were told bears are out there for one reason, find food, and you are food. So that is a problem for doing research on the sea ice. So why are we doing climate research in the Arctic? And why is it so important? And how does the Arctic affect the climate in the globe? And, of course, last question kind of answers a little bit the first two questions, or suggests an answer to the first two questions. We're scientists. We want to advance scientific understanding of a very unique environment. The Arctic is a unique environment. And so we are trying to improve the understanding of physical processes and their interconnections, and to apply this understanding to computer models. So that could include the global climate models that are making these global warming predictions, also operational weather and sea ice forecasting models, and other types of environmental models. So that's the way you apply the understanding you get from making the measurements and trying to understand the physical processes. We're also trying to document the Arctic climate change and understand the processes that are producing this change. One of the main points is that the warming predicted to be, and is, amplified in the Arctic compared to the rest of the globe. That is, it's what's called an Arctic amplification to the global warming. So this is a map showing the globe and this is a observed temperature change from 1960 to 2011. It's a combination of satellite images or satellite data and surface observational data, but it makes the point that if you're looking here, the Arctic region has warmed by 2 to 4 degrees since 1960. The northern hemisphere by 1 to 2 degrees. So there's a doubling, basically, at least, of the surface temperature in Arctic over the northern hemisphere. And globally, it's more than doubled in the Arctic compared to the global changes. So clearly, the Arctic is a kind of a canary in the coal mine, so to speak. It's changing much more rapidly than the rest of the globe, and we need to understand that part. We also need to understand the globe, but that's clearly a very key portion here of the whole picture. And I want to point out that sea ice loss is a very key change happening in the Arctic, and provides a positive feedback to the climate change in the Arctic. And I will get back to that in a later slide. There's also been hypotheses put forward based on some observations, but a lot of work still needs to be done. But these hypotheses suggest that the Arctic climate change may have significant impacts on global weather and climate. So feedbacks to the mid-latitude jet streams and release of large stores of carbon dioxide and methane in particular, but greenhouse gases in the Arctic permafrost. That would provide a positive feedback to the whole global climate warming due to the greenhouse gases. So that's potentially a very important impact on the globe that the Arctic changes can have. Finally, the climate change, especially the reduction in the sea ice cover, has significant impacts on the Arctic itself. And for mineral and energy exploration and exploitation, marine oil deposits and terrestrial minerals, for instance, surface transportation, so opening the northeast and northwest passages and the trans-Arctic routes, making transportation and shipping much quicker for different parts of the world, especially for, say, Europe to Japan or something like that. So that's potentially very important. And has impacting the indigenous livelihoods. Their lifestyles depend on the predictable ice and weather conditions, and that ice and weather conditions are changing. And they can no longer use their knowledge of that to say when they need to do various things in their community. And it's also impacting tourism. It's more popular now to go to the Arctic. And for instance, Russia now has a nuclear icebreaker that if you have enough money, they will take you to the North Pole. And just so you can say you've been to the North Pole. So those are kind of a summary of why we're doing climate research in the Arctic. And then getting into some of the details of some of that, clearly I mentioned that the sea ice change is a very important aspect here. And so this shows satellite images from 2002 to this fall in September, the sea ice extent. There's slightly different types of images, but they all show the same thing, the sea ice extent in September, mid-September. And the pink line shows the median September sea ice extent from 1979 to 2000. You see, during this entire time, there was less sea ice than during the late 20th century. But there's clearly variability for each year, 2007 being a very low year, 2012 being slightly even lower, and other years that not nearly as much of a meltback. But one of the things to note is that much of the meltback is occurring in the Siberian seas and the Beaufort and Chukchi Sea regions here north of Alaska and the Bering Strait, while a lot less over on the Atlantic side.
What's the hypothesis for that?
I will get to some of those hypotheses later on. And some of them are consistent with this, others are not. So if you look at this pink line, compare the colored area to the pink line, or here just the white area to the pink line. Oh, so the satellite observations I just showed you, and even further back into around 1970 or so, when satellite data started to become available and we could do those kind of measurements. In red here shows the September sea ice extent in square kilometers. This is now in millions of square kilometers. And we see that for about a decade or so, it was fairly constant, and then it started dropping off and dropping off. It's a lot of variability from year to year. 2007 here, very low. 2012, even lower. And last September, we actually rebounded a bit. But clearly, there's a very strong decrease in this aerial sea ice extent. What's interesting then is to compare that to these climate models. And their predictions, they start the climate models back in the 19th century and then see how well they do compared to the current observations, and then how take them out into the future. And there's 13 climate models from different institutes around the globe. They're all in these dotted lines here in the background. The black line is their ensemble mean, or in other words, their average. And you can see that the average did a pretty good job of estimating roughly where the observed sea ice cover was in the latter part of the 20th century. And the prediction is that the sea ice extent will decrease significantly by the end of this century. And you can see that a lot of different models, it's a lot of variability between the models, but none of them show an increase or even a constant level of sea ice. They all show a decrease. There is obviously, because of the differences between the different models, quite a bit of uncertainty in how rapidly this decrease will occur. Another important aspect to look at here is that the Arctic sea ice extent the observed Arctic sea ice extent is decreasing much more rapidly than any of the computer models, suggesting that there are some processes in these models that we're not getting right. And unfortunately, it's processes that are producing even larger decreases than what's observed. And so clearly there's definitely room for improvement, both to improve the variability between the different models and to improve the matching with the observed sea ice trend. Some other observations showing that thickness has decreased dramatically. The wintertime thickness is 3.5 to 4 meters back in around 1980, and fall thickness 2.5 to 3 meters, and now it's more like 1 meter in the fall and 2 meters in the winter. So clearly the thickness has changed dramatically. People did some calculations and suggested that this amount of ice mass change, both the aerial change and the thickness change, can be accounted for by a net change of 1.2 watts per square meter energy flux to the sea ice. So keep that number, roughly that 1 to 2 watts per square meter in mind, because I'll point that out in some other measurements, which are typically much larger than this. So you can see that this is really what we need to look at, and that's the accuracy we need.
Can you explain what the energy flux means?
Okay, I will explain that in a little bit, actually. But basically, energy flux, you have a slab of sea ice, and you have energy coming from the atmosphere or from the ocean to it. So that net energy flux, both from the atmosphere and ocean combined, that would be, say, how much can melt. So if you have energy flux of 1.2 watts per square meter, well, actually, if you have energy flux of 10 watts per square meter to a slab of ice for 1 year, you melt 1 meter of that ice. So 1 watt per square meter melts a tenth of a meter, or a decimeter. They generally look at freeboard. They get basically an altimeter. This is one of the ways, at least. So they measure the height to the ice, and then find an open water area around that, and measure the height to that. And they can see the difference in freeboard. And so that freeboard, then they know what the density of ice is. So then they can figure out how much should be showing above the water. And so that freeboard then tells them how thick that ice is. This usually it was military submarines, and they had sonar. They were trying to see where they could go up, but they had a lot of sonar data that was classified for a long time, but then in the last 20 years or so that was declassified, and scientists used that to then go back to find out what the thickness trends were. Impacts on global weather and climate. So as I mentioned, in the Beaufort-Chukchi Sea regions, there's typically much more open water now than there used to be in the late summer and in the fall. This produces heat back to the atmosphere that then increases what's called the height of the atmosphere. So in essence, puts a high-pressure system at mid-levels in the atmosphere over Alaska, Western Canada, and over the Beaufort Sea and Chukchi Sea regions. This then produces a resulting northerly flow towards the south in the central and eastern North America. And this would happen in the late fall and early winter time periods. And exactly the feedback and quantifying this feedback hasn't really been done yet, but there are suggestions. For instance, you've all heard of this polar vortex this winter. And what that's all about is typically you have a cold air centered over the Arctic region and fairly cohesive single-centered region, and the jet stream is at the boundaries, and that's where you get the storms. And sometimes this cohesive single-centered polar vortex breaks down into this fragmented, or what they call wavy, polar vortex. It causes these mid-latitude intrusions, and this happened to be now early January of this year, last month. And this is a weather chart from that, showing the high-pressure system going all the way up into the Beaufort-Chukchi Sea regions, and the northerly flow coming in and bringing this cold air mass down into the central and eastern United States. And if you look carefully, these are also surface pressure areas shown here. There's a storm here, basically over Toronto or so, along the east coast. At this particular time, this has happened to be January 6th. So, but there were other centers around the globe too that had these cold air outbreaks. So this is one possible suggested feedback to the mid-latitude weather that may be happening because of changes in the Arctic. Yeah.
Does the polar vortex exist winter long, like for an entire season, or does it kind of fluctuate?
Well, this fluctuation like this from a single center to a fragment or wavy pattern, that fluctuation has happened before, but this fluctuation to this pattern seems to be happening more often now. And this is what people are pointing to, saying, well, maybe this is caused by these changes in the Arctic Ocean. It hasn't been proven, but it's a suggested hypothesis, and has drawn a lot of press apparently, especially in the East Coast. Professor Rutgers talked about this.
Quick question. So is the thought that if the Arctic warms, will the location of the jet stream kind of, will that circle kind of increase in size and move further south?
Well, I don't think people have really thought that far yet. I don't think that would have happened, but the point is that because there's a regional warming here in the Beaufort-Chukchi Sea region, that is introducing a instigator of making this wavy pattern.
So the jet stream as a whole probably won't expand outward, but little bumps of it will kind of
Right.
get further down than they might otherwise.
And like what happened here in January, yeah. And what's probably going to be happening next week as well, according to the forecast. Well, again for the East Coast, not for us. So, but this is an interesting hypothesis, at least, and it's being tested by lots of people, and it's one of the hot topics of research at this point. And we don't know, no one's quantified how much heat is actually coming out of the ocean up there in the autumn. And I hope to be on a project in 2015 to do that, actually. But it takes time to plan all this stuff. And then other impacts include this release of greenhouse gases from the permafrost in the Arctic. And for instance, here in the Arctic, the eastern Siberian seas of the Arctic Ocean, there's deposits of gas hydrates, and some regions are now thawing. And there have been observations right here of bubbles coming up, and they're sampled, and it's methane. There's also some carbon dioxide ones as well. And so, but nobody knows how much of these deposits are thawing and how much gas is coming out of them. There's estimates of how much there might be up there, and it's quite large. And so it could be tremendous feedback impact for the globe. So what do scientists measure in the Arctic? Where do they make the measurements? What instruments or tools do they use? And what are some of the challenges of Arctic research? People have been trying to make measurements in the Arctic. This is now atmospheric measurements all the way since 1890s. Fridtjof Nansen, a Norwegian oceanographer, was the first one to really have a scientific expedition to the North Pole, not just a political one trying to get to the North Pole. But his was pure, much more scientific, and using a wooden ship, the Fram. And if you go to Oslo sometime, you should go to the museum. It's a very interesting museum. And they froze in 1893 and drifted across the Arctic Ocean and came out here near Svalbard in 1896. So 3 years, and they have hourly atmospheric measurements. And I'll show you their instruments in a little bit. But they had 3 atmospheric scientists, 8-hour shifts for 3 years. That's dedication. Nansen was an oceanographer. He devised some very unique ways of measuring ocean temperatures, and he has ocean temperature data all the way across here as well during that time period. The Soviets had a lot of drifting ice stations, and that was continued by the Russians starting in the early 2000s. And a couple of their tracks, their drift tracks are shown here. There's some American ones, and the Sheba used a fair bit of data from there because our laboratory was participated in that one. And actually, this LEADX was that opening photograph I showed you of the Beaufort Sea ice. And then there have been recently some Swedish-led expeditions with their icebreaker. There's series of 4 of them, typically summer expeditions, but up to near the North Pole to look at some of the processes there. There are some other ones too I didn't have room to put on here. As I mentioned, there are stations around the Arctic, around the periphery of the Arctic, on land sites, terrestrial sites, that are making extensive measurements. Eureka is right here. It's one of them. Alert, both on Ellesmere Island, Summit, New Ålesund on Svalbard, couple, one in northern Sweden, and Sodankylä in northern Finland, Tiksi, northern Russia, and Shetski, and of course Barrow. Here's some of the measurement techniques. This is from the Norwegian 1896 expedition. Manual wind observations, manual temperature and humidity and surface pressure observations, hourly. Sextant to get their location in ice drift, and Nansen making his temperature measurements in the ocean, the temperature profiles. We have more modern techniques now. We put out towers and data loggers. Helps a lot. And these are, we put them out on the sea ice and also on land. This is the one at Eureka that you've seen pictures of many times. And some of these instruments measure the wind components, the 3 wind components, for instance, and temperature components, and humidity components, and also carbon dioxide components at up to 40 times per second. So we really need data loggers. And we need that high frequency to measure the turbulence, because the wind gusts, for instance, and especially the vertical variations in wind, or variations in vertical wind, are all very important here. And so to estimate the turbulent fluxes. Radiation, extremely important. I'm not sure. Oh, well, this isn't really radiation. This is just show an automated station measuring radiation and turbulence. but also we had to use some innovative power supplies, so wind energy and solar panels to get power to our systems. But radiation measurements, this is now how you get the albedo. This is looking at the upwelling shortwave radiation from this radiometer, upwelling longwave radiation from this radiometer. And there's another mast right behind the photographer here measuring the downwelling part, so turning those identical instruments looking upwards. And then there's also an acoustical device measuring snow depth looking down at the surface. So this is what's called an albedo rack. This is one of the Swedish expeditions out near the North Pole. There they have the 4 components all on one unit here for the radiation.
Doesn't the rime ice kind of mess with that, or no?
It does, and this is why this is an important reason why automated radiation and surface energy budget stations have not yet been devised, because we cannot get rid of that rime ice off the radiometers except by elbow grease and very careful felt cloth. So, and then to look at the clouds, look at using radars, microwave radiometers and salometers, for instance. So both typically they end up being on icebreakers on ships, and because they're big instruments. So these are the cloud radars. This is actually a precipitation radar, cloud and precipitation radar, and salometer and these radiometers here all provide important pieces of the whole picture. This is the cloud radar at Eureka, down by the side of the fjord there, showing some of the images and data of the cloud properties. And that has been there for 8 years now. These remote sensors can also measure other properties of the atmosphere, for instance, wind. So this wind profiler, we're the first one to put one of these large, this is 8 by 8 meters, so 24 by 24 feet platform that this wind profile sits on. We're the first ones to put one of these on a ship on that Swedish icebreaker, but we got some very useful, interesting data with that. It gives us hourly wind profiles, or no, I'm sorry, half hourly is what we're running at. And other profilers, radiometers, for instance, can get some estimates of temperature profiles at much higher temporal resolution than you can get from sending up a balloon, which is typically at most every 3 hours you can do that, but you can't do it that frequently for very long. Other remote sensors include SODARs. Again, this is the Swedish icebreaker Oden here that we've been using a fair bit to get it into the pack ice. Also, not just launching a weather balloon that is lost, but we'll also have tether sondes here. And so here is a 2-week period in late August of 2008. Having graduate students helps a lot. So you get a lot of profiles, so they have to run the winch to send this balloon up and down and getting these temperature, humidity, and wind profiles, and also aerosol profiles too. Also, you can get data that is of very good quality, but more sporadic because it's so expensive to use them. But you can use aircraft, of course, or helicopters to make some of these measurements also. You really have to be careful about ingesting, for instance, aerosol from the aircraft into your samples, or wind measurements from helicopters in particular. Or you can combine, and this is a method we're using a fair bit, is combining a bunch of different measurements. So satellite measurements. This is now a satellite image. Near North Pole is just about up here. The Swedish icebreaker is here on this blue line. And this red track is this NASA DC-8 aircraft track. And so we can get, for instance, satellite image here, detailed information from the track of the aircraft, which is the blue line in this part image here. This is the cloud radar image, and showing, for instance, these precipitation shafts of snow through this deeper cloud system here. So those kind of detailed information you can get by combining data sets. The ice mass balance, thickness, is of course, varies during the year as well as the extent of it. And so you have growth at the bottom of the sea ice in late fall into the winter, and then rapid melt both at the bottom and at the top. And notice that ice does not grow on top at all. You get some snow on top, but there's no ice that grows on top of the sea ice. It's all growth is on the bottom. And then hopefully the ice survives the summer melt, and so in this case it did a little bit, about 60 centimeters or so. And then you get more growth in the late autumn into winter, and then again the melt from the bottom and from the top in the following summer. To get these kind of measurements, oh, and these colors here indicate the temperature within the sea ice. To get these kind of measurements, people at this Coastal Regions Research and Engineering Laboratory in New Hampshire have devised this ice mass balance buoy, which uses an acoustic sensor both at the top and at the bottom to look at what happens to the surface, both the bottom surface and the top surface, and then a thermistor string that goes down through the sea ice to measure the temperature profile. So in real life, looking at it from the top here, this is what it looks like. So it's really a very useful instrument, and they try to put out one of those near the North Pole each April or so. And they survive maybe a year, and then they get broken up. Other problems. We talked about the rhyming problem, and definitely can be a major problem getting good data for the surface energy budget. And this is on the sonic anemometers, that measure the turbulence, and on the radiometers, both. Other problems are logistics, access to here. You have to get out there with an icebreaker, but you try to get someplace with your snowmobile, and you can only go so far. You have these melt ponds and such, and so access is a problem. Access for another reason is polar bears. You don't want to be out there at the same time, and they're very curious, and they want to be around. Everybody has to walk around with rifles, or have different ships run it differently. Some people allow scientists with rifles, which question is whether that's dangerous or not. I would say it is maybe, but or other people say they have to have armed guards with them so from the ship itself. Other issues is when these flows come crashing together. So this one of our automated stations got caught up in one of those and got totally smashed. Moving sea ice. It's basically plate tectonics in fast motion. It can happen in 20 minutes. And so the Fram in 1890s was wedged in between flows. In the 1970s, from the University of Washington program, a lead opened up right underneath their mess hall. And I like Norbert Untersteiner's comment, people did not linger over dinner. At the Sheba site, a lead opened up right through the camp, and these power lines and so on had to be cut very quickly, because it happened in about 20 minutes, and launched one of these two sides came together, launched one of the snowmobile huts up into the air. Luckily, there was nobody in there. For difficult environment, at minus 40, you don't have much time to even turn a nut or something like that when you're adjusting instruments. Getting around is a bit difficult. This truck, you can see, has triangular tread wheels. But one does the best that one can. I also find out eyeglasses do not work at all, so I'm partially blind when I go up there. Resupplying is an important issue. Can typically either do with icebreaker or with aircraft to some of these sites. So what have we learned so far? It's a whole long list, and I'm not going to go through all the details here, but there's a few main points, and these main points even are still limited and, as I mentioned, atmospheric-centric list because of my own background. But probably the most important aspect that we have learned is that processes in the atmosphere, cryosphere, ocean, and pedosphere, the soil it is, interact, and it must be considered, all of them together must be considered as a whole system. And doing research or measurements in just one will leave you asking questions that are related to the other spheres and you still won't understand how it really works unless you take into account the other systems. And scientists are just learning that, and that interaction is kind of slow in progress. It means people have to get out of their comfort zones, their areas of expertise, and talk to other people and try to understand what they're saying and doing. But some of the results that I can say has been learned so far is that we've begun to quantify atmospheric and surface energy fluxes determining the evolution of the sea ice and presumably permafrost. And we find that all terms have significant magnitudes and variability. Their cryospheric properties, such as albedo and snow cover, are very important for interactions with the atmosphere and the ocean. Processes in both the atmosphere and the ocean may be directly causing the observed changes in the sea ice. And I'll talk about each of these a little bit more in detail in the next few slides. And the feedback processes are important for enhancing Arctic changes and producing the global impacts. I talked a little bit about the global impacts here before. So one of the proposed oceanographic mechanisms for disappearing Arctic sea ice is that there's warming of the mid-depths, so around 300 meters deep. Atlantic waters are entering the Arctic Ocean and circulating in the Arctic. This water eventually comes out again at the through the Fram Strait. It enters in through the Barents Sea and the eastern edge of the Fram Strait. However, so people have seen that this water has been warming. They make measurements in a couple of locations here and here, and they've seen that this water has been warming in the last couple decades. However, there's only minimal amounts of this heat appears to be reaching the bottom of the sea ice. So in other words, it's not coming up from this 300-meter depth. And so this is a problem. And the few places where they have seen it coming up tends to be on this side. And of course, we've seen the big changes occurring over here. So this may not be the answer, but it is something oceanographers are pointing to is a potential ticking time bomb, because if this warmer water eventually does get up to the bottom of the sea ice, that sea ice could go really fast. Another mechanism that was proposed in the early 2000s was that have been large-scale wind and ice drift changes occurring. So, for instance, here in 1979, there's this Beaufort gyre. This is now ice tracks. They put buoys on the ice and track them with satellite, and see that there was typically a large recirculation in this Beaufort gyre. This is now Alaska here, and here's the Fram Strait here. Some ice went up the Fram Strait, but most of it recirculated, and therefore the ice. This is now ice age. The ice was quite old and thick in much of the Arctic Ocean. However, in the late 1980s and 1990s, this circulation changed and now was more of a counterclockwise circulation and coming out with a lot of ice coming out through the Fram Strait and only very little recirculation here. And so the net result was that the ice thickness decreased substantially between those two time periods, and the ice age as well. So the old ice is kind of relegated to the top of the Canadian archipelago and in Greenland, and the rest of the Arctic Ocean has much younger ice. So people are pointing to this large-scale wind changes as being the cause. However, since the 1990s, the wind patterns have changed back to what they were before, but sea ice decline has continued. So they're saying, okay, well, maybe that wasn't the entire answer, at least. It might have been part of it. And then there's an atmospheric thermodynamic mechanism, melt of the sea ice. One problem was that we didn't really understand what that was at all. And so we're starting to get a little better handle on that now, and we're seeing it's a very complex and very sensitive system of atmospheric energy fluxes, and that this might be modified by changing heat and moisture transport from lower latitudes. However, it's both difficult to quantify both the changes and in the transport and in the energy fluxes. So to illustrate the complexity and how the system works, I have this schematic diagram, basically of the energy budget in a vertical column over the Arctic sea ice region. And we have in the blue here, dark blue, long wave radiation. So for instance, important aspects are how much long wave radiation going down to the sea ice, how much coming back to the clouds, and then how much is being lost to space. Also the short wave radiation, how much is penetrating through the clouds. Well, obviously, we know it's coming from the sun, but how much is coming through the clouds and then being reflected back to the atmosphere or being absorbed by the surface. Again, this is now the function of the surface albedo. And then there's also other components like the turbulent energy fluxes here, for instance. The net energy flux, if you're going to have a steady-state system, has to be 0. Now, these numbers are quite large. And remember, a 1 or 2 watt per square meter change can have a significant change. So how well do we know these? We don't know them to the 1 to 2 watt per square meter value. So this is a problem. And we also argue that our models aren't able to reproduce these fluxes to 1 or 2 watts per square meter error. And so we have ice albedo and cloud feedbacks can also greatly impact the surface energy fluxes. And I want to illustrate that. Here we have the same budget again with the 0 net energy flux. If we take away the sea ice, we see changes occur in the amount of energy, solar radiation absorbed by the surface because the albedo has changed dramatically at the surface. There's some changes in the long-wave radiation as well, and also in the turbulent heat fluxes, but the net effect is that there's an increase of energy flux to the surface. So that albedo that the sea ice provides is extremely important. If we remove that sea ice, we get a positive feedback, so more energy coming into the system and more warming. If instead we remove the clouds, now we change also the amount of solar radiation reaching the surface, but because of the high albedo, a lot of that is reflected. But the more important change is over here in the downwelling long-wave radiation, very large decrease, and the net result is a very large decrease in the net energy flux at the surface. And so if you remove the clouds, you'd have cooling at the surface. Or if you enhance the clouds, you'd have warming at the surface. So clearly, both the clouds and the sea ice are extremely important components of the system. Are we? Yeah, okay. I've got a couple more here. Okay. One of the processes that the feedback processes that oceanographers point to recently has been this recent formation of this near-surface temperature maximum at about 20 meters, typically in the Beaufort-Chukchi Sea regions, where the ice is either gone or very thin. And they point to that this heat, this is a new feature that hadn't been in their profiles before, the last decade or 15 years or so. They point to that this heat can then be available for later release to the atmosphere. We talked about that some, and the impacts of that for lower latitudes, and to the underside of the ice. So they believe, and the evidence isn't totally there yet, but there's some suggestions that the sea ice growth underneath the ice is being delayed. And they point to this near-surface temperature maximum as being perhaps the cause of that, the energy source for that. So there's a feedback mechanism built into happening in the system here because of the loss of sea ice in this region. This is related to that in that how that release happens is also uncertain. And so this is a Japanese ship that was up there in 2010 and measured, this is now Barra right here, they measured the upper ocean temperatures along this line here in mid-September and found quite warm temperatures in the upper 20 meters or so of the ocean. They came back 2 weeks later and 4 days after this large storm went through this region and found that the temperatures had dropped by over 2 degrees in this upper ocean. That's a lot of heat loss, actually, because of the large heat capacity of water. And so, and they're saying that this was caused by the passage of the storm and the strong winds with the storm. We don't know whether that is a typical process that happens or not, or whether it's more kind of a long, drawn-out process. And this is one of the things that people are trying to quantify, how this heat loss occurs. At the Shiba site, that began our ability to quantify the atmospheric and surface energy fluxes determining the evolution of sea ice. And generally what was found was that all terms have significant magnitudes and variability, and the summer ice melt correlates well with the net energy flux. So if we look at net energy flux rather than, say, temperature, we actually get a good matchup with the changes in the sea ice amount. The blue line here, this is now directly observations. The blue line shows the net energy flux during the winter being slightly negative during much of the winter, about 20 watts per square meter. Summertime, it's up to about 85 watts per square meter. I mean, these are much larger numbers, but the annual average is what really determines the net result for the year for the sea ice. But clearly, this matches with the growth of the sea ice here, then the melt at the top of the sea ice here in the summer. These large variability, up to 50 watts per square meter over a few days, that seems to be associated with storms and clouds. And so they greatly modulate this energy flux. And this occurs year-round. And so if the frequency of these events or the impacts of the impact amplitudes of these events changes, this could impact the net energy flux to the extent to have a significant impact on the net energy flux for the year. So this is some of the processes that is also being looked at. This is an example of moisture coming in through the Fram Strait in the atmosphere, seen by satellite, coming over to the Shiba site. This warm, moist air comes in aloft. Clouds are associated with them. Where those clouds are, you see the pink line here, the long wave radiated fluxes. This is now winter, so there's no solar flux here at all. The long wave radiated fluxes increased tremendously by 90 watts per square meter or so, associated with the fluxes. It's actually associated with liquid in these clouds. This is measured by the radiometers, showing that the clouds, both the deep ones and the shallow ones, have liquid in them. And these liquid cloud events produces temperature warming in the sea ice, and this warming in the sea ice then propagates downward through the sea ice, and it's remembered in the sea ice. So it impacts, we think it may impact then when the melt starts in the spring. So there's a lot of processes going on here, from long wave transport to the cloud structure and the phase of the clouds, whether they're liquid or ice, and then the thermal structure in the sea ice itself. And the clouds we're talking about can be those deep ones, which are fairly infrequent, but the more frequent ones are these stratocumulus clouds, fairly shallow, low-level clouds, but if they have liquid in them, they become very important. Similar types of measurements, of course, are being made at Eureka and Alert. This is just an example for 2 years at Eureka, showing a year with fairly shallow snow depth in the spring, another year with deeper snow, and the impacts it has on the summer active layer in the soil. So in other words, when the temperature is above freezing in the soil. And the onset for the shallow snow year was earlier of the active layer. The depth of the active layer was 7 centimeters deeper than it was during the year where the snow was deeper. Again, similar types of comparisons to Alert are done, and there the difference is about 30 days rather than just, in this case, just a handful of days at Eureka. Yep. And finally, this is our Eureka Tower. And I did show before the surface energy budget in the previous slide, but here I want to just point out the carbon dioxide flux measurements that are being made. So we have begun making the measurements of the release of these greenhouse gases from the permafrost, but the signs and magnitudes are still uncertain. We're starting to get some idea of how it's operating, at least at Eureka. For instance, here, this shows a 24-hour period in the autumn. I believe it's a 2007, if I remember right. And we see that during daytime, there's upward moisture flux and downward carbon dioxide flux. So soil is a sink for the carbon dioxide in the atmosphere, while at nighttime, the soil seems to be a source for the carbon dioxide. So it's coming out of the soil at night. When the temperature then goes below freezing, so the biological activity decreases substantially, now the carbon dioxide is almost entirely coming out of the soil. So the soil is a source of carbon dioxide during that time. But if we look at the entire year, in general, it looks like the soil is a sink of carbon dioxide, not a source. So either the permafrost is not thawing substantially there at Eureka yet, or we don't have long enough time series of it. And so right now, at least, it looks like the soil there seems to be a sink for carbon dioxide.
May I ask, when you talk about the soil, do you mean plant activity is taking carbon dioxide, or the soil itself?
The soil, what's going down into the soil? Yeah. We're not measuring methane here. Yeah, we're just measuring carbon dioxide with a particular instrument we have. We didn't have the money to put out that instrument. And measuring the greenhouse gases was basically a secondary activity to measuring the surface energy budget, at least in our proposal that we got funded for. So, yes, yes. So this is basically, in summary, again, just a pretty shot of the mountains off in the distance at Eureka, but repeating some of what I've already said. But the changes in the Arctic and some of the key things that we've learned, that the Arctic environment is closely linked physical system with interdependent atmospheric, cryospheric, oceanographic, and terrestrial processes. And the warming effect from clouds is underestimated by climate models, especially during winter. So we saw that was an important process, and we know the models don't handle this very well right now. So that's another area of research. And the changing Arctic and its impact on our societies, or the societies up there, is very important also.